Since 2020, artificial intelligence has advanced with massive, unstoppable momentum. But right now, that momentum is hitting a physical wall. For years, the industry relied on a simple equation called an extrinsic scaling law. To build a smarter model, researchers combined more training tokens with more raw computing power. This graph plots model performance against data and compute. The line rises smoothly, but crashes into a vertical limit at 50 trillion tokens, the approximate total of high-quality human text available on Earth. Researchers cannot simply synthesize or scrape another 50 trillion tokens of equal quality to keep the curve moving. The supply of premium human data is finite. At the GTC 2026 conference, Jilin Yang, co-founder of Moonshot AI, presented a solution to this data bottleneck. His team built Kimi K2.5 by shifting the industry focus toward intrinsic efficiency, extracting more intelligence from the exact same volume of data. Future progress depends on engineering architectures that can mathematically double the intelligence gathered from existing datasets. When a neural network trains, it uses an algorithm called an optimizer to adjust billions of internal weight settings based on mathematical feedback about its errors. Since 2014, the AI industry has relied almost exclusively on a single default optimizer, known as Atom. This diagram illustrates a structural flaw in the Atom optimizer. Each arrow represents a weight adjustment. They point haphazardly and cross over each other, meaning the model performs redundant learning work and wastes compute. Moonshot AI replaced Atom with a new optimizer called Muon. Muon forces every weight adjustment to be mathematically independent. It points each nudge in a distinct direction, ensuring the model covers unique parameter space without overlap. Swapping algorithms produced a measurable result, a 2x improvement in raw token efficiency. With a 2x efficiency multiplier, a dataset of 50 trillion tokens mathematically functions as 100 trillion tokens. The data supply remained the same, but the ceiling broke. Applying the Muon optimizer to a massive 1 trillion parameter model introduced a severe operational bottleneck. This chart tracks model loss during training. It descends smoothly until hitting a phenomenon called max logit instability, an uncontrolled explosion in the mathematical confidence scores of the model's predictions. That mathematical explosion shatters the training process and destroys the model's learned progress. To solve this, the Moonshot team engineered a real-time algorithmic constraint mechanism called QK-clip. QK-clip applies a gentle limit. It bounds the confidence scores into a safe range without dampening the model's ability to learn. Because of this fix, the Kimi K2.5 training run processed 15 trillion tokens without a single loss spike. These training curves prove that optimization breakthroughs require highly engineered stability mechanisms to survive at scale. Beyond raw training efficiency, a model must maintain massive operational memory capacity, known as its context length. This grid visualizes the computational wall inherent to standard transformer full attention. It requires red connection lines from every single node to every other node. The computational cost scales quadratically. Quadratic scaling ensures that parsing massive codebases or entire textbooks in a single prompt is computationally impossible for standard models. Moonshot engineered a hybrid architectural solution to bypass this limit, naming it Kimi Linear Attention. Kimi Linear mixes efficient linear attention with standard full attention in a 1:3 ratio. The model retains the reasoning benefits of full attention at a fraction of the cost. Within that linear attention component, the team developed a secondary breakthrough regarding memory decay. Previous linear models applied a single global memory decay rate to all data. K2.5 breaks that dial into many independent ones. It assigns specific decay rates to different channels, allowing some to refresh quickly while others retain data across vast context lengths. Infinite context approximation relies on the specific algorithmic logic of determining exactly what the model is allowed to forget. Executing a massively complex prompt requires a highly coordinated multi-agent environment to handle many distinct parallel tasks simultaneously. Moonshot structurally shifted the deployment of their model away from monolithic inference into what they term agent swarms. This diagram outlines the hierarchy. A central orchestrator node receives the prompt, decomposes it into subtasks, and assigns them to specialized subagents working in parallel. This delegation behavior had to be explicitly trained using 3 distinct reward signals. The first signal rewarded the model for spawning subagents, preventing a failure state called serial collapse, where the orchestrator attempts to do everything itself. The second signal rewarded the orchestrator for tracking the subtasks and ensuring they were actually completed, rather than just created and abandoned. The third signal evaluated the final outcome, rewarding the orchestrator's ability to seamlessly synthesize the returning data into a single, accurate answer. Elite task execution requires moving completely beyond single monolithic minds into a framework of meticulously trained, verifiable delegation. The final dimension of K2.5's construction involves its multimodal data intake architecture. The industry standard is a retrofit approach, pre-train the model on text and bolting on vision modules afterward. K2.5 utilizes an early fusion protocol, where vision and text data are mathematically woven together from the very first token of training. This produced a counterintuitive finding. Training the model on purely visual tasks significantly improved its performance on abstract, text-only reasoning. It also led to a second phenomenon that the Moonshot team termed zero-vision supervised fine-tuning. Because of the shared representation built through early fusion, the model achieved near state-of-the-art visual benchmarks with essentially zero dedicated visual training data. Visual processing acts as a direct catalyst for abstract reasoning, proving that image data significantly enhances a model's underlying logical foundation. By combining muon for efficiency, QK-clip for stability, Kimi linear for context, and early fusion for reasoning, K2.5 achieves massive coordinated performance gains. At GTC, Jilin Yang previewed the MEX structural frontier for his team's architecture. This animation shows the historical function of residual connections. Arrows explicitly loop around individual layers to pass data sequentially downward, which prevents the training signal from collapsing in deep networks. Mathematically, a residual connection is a recurrent network rotated 90 degrees through the architecture's depth. They created a tension residue. Instead of adding only to the previous output, a deep layer attends to all previous layers' output simultaneously. Preliminary results show that a tension residue yields an immediate 24